The next charge distribution that we'll look at is the thin ring of charge. And you can imagine that this thin ring of charge is a lot like the rod that we've just bent around in a circle. And so with the rod, we had to add up along the length of the rod. Now we're going to add up point charges around the circumference of the circle. And so the first thing we do is we cut up the distribution into pieces so that we have point charges at particular locations on the ring, and we can locate the vector that describes where those point charges are on the ring. So in this case, the ring is drawn in the XY plane, and the point charge exists at some angle theta and at some radius r on the ring. And then we want to know what is the electric field at some observation point that's on the z-axis. And so the first question is, how do we write down the position of a point on the ring and where that ring point is relative to the observation point? So what is the vector that describes going from this point on the ring to this observation point? Once we know that vector, we're going to then normalize it to calculate the r hat vector. So how do we do that? Okay, we know that on the circle, the position of the charge that we're currently interested in calculating will have a vector position that's described by the radius and the angle. And so in the xy plane, what we'll have is that the r vector is going to be the radius of the circle times cosine of theta along the x direction, r sine of theta along the y direction, and because this is in the xy plane, this has no z component. And then we have an observational point that's located on the z-axis. And so then the r vector that we're interested in knowing, so maybe I'll call this rq, is going to be the difference between the endpoint where we're observing and the point where the charge of interest is. And so that position is going to be just the subtraction of these two vectors. Let me clean that up. And we can calculate the magnitude of that using the Pythagorean theorem. And this can be simplified because I can factor out of the first two terms, I can factor the r squared. So that this term is just 1, and that means that the length of this vector is just r squared plus z squared. And that means that we have unit vector describing the direction of the electric field that's going to be produced from this positive point charge is just going to be the ratio of the vector itself to the magnitude of the vector. Once we have our R vectors, we're ready to write down the electric field of a point charge and insert all of those vectors so that it becomes generalized for any of the point charges along the ring. So we know that for a point charge, the electric field is 1 over 4 pi epsilon naught Q divided by R squared. And if we want to write the vector, we just put a vector over the E and add the R hat, which tells us the direction of the electric field. Now, what we're interested in is each point charge is going to contribute some increment to the electric field, and so we rewrite this as adding incremental charge to the electric field. And then we do our substitution. So we have this R vector here, which we actually don't even need, because what we do is we normalize that to get the hat vector, and then we have an R squared in the denominator, so we need to use this. So that just means that I can write delta E as a vector is 1 over 4 pi epsilon naught delta Q, and then I square my R so that I have R squared plus Z squared, just getting rid of the square root, and then I have R hat and again I can combine these denominators so that I get R squared plus Z squared to the 3 halves. One thing to keep in mind is when you make that combination, you're now no longer in a form where you have a hat vector over here on the right hand side, so you just want to keep that in mind, that this vector is no longer a unit vector because we've made a combination of that denominator. Okay, so the next step is it's not very easy to add up increments of charge, and so we really want to add up over some sort of geometrical factor, so in this case over the circumference of the circle. And so what we want to do is rewrite delta Q so that we can make it geometrical. And so remember that if we have some amount of charge that's here out at the radius, that the small amount of the circle that charge takes up in terms of length is going to be the radius times the change in angle, and this is in radians. This is very important to remember that this doesn't work in any other units. And we know also that when delta theta is 2 pi, that we get the circumference of the circle. So we know the length of that distance around the circle is 2 pi r. That's just delta theta times the radius. And so we can write down our charge density for this circle. Which we write down as a charge per length. And we know that that's equal to the total charge that's in the circumference of the circle. And so if I solve for delta Q, let me write it in the same order. Delta theta divided by 2 pi r. And my r's will cancel. And I can write down my charge increment as the total charge times the change in the angle divided by 2 pi. So we know that when the change in angle goes to 2 pi, we're going to get that the delta Q has added up to the entire charge in the ring. Okay, let's put all the pieces together. We have this form for the point charge, 1 over 4 pi epsilon naught delta Q over r squared in the r hat direction. And we've already found what r squared and r hat are, and we just found what delta Q is, so we can just plug all those things in. So plugging in for delta Q, and then I found earlier that 1 over r squared times r hat gives us an r squared plus z squared to the 3 halves. And then our vector minus r cosine theta minus r sine theta z. And so our summation variable is delta theta. So we're going to be adding up all of the contributions around the ring as we increase theta by some increment delta theta. But before we worry about doing that, let's take a look at the problem again. And so in the xy plane, we have this ring of charge, and if I put a charge on this side, and let's say it's positive, it will have an electric field that points away from it in all directions, but I'm considering along the z-axis, which points towards us from the origin here. And so I want to know in the xy plane, how does the electric field look if I'm on the z-axis? And so if I put another charge on the opposite side of the circle here, which there will be one because we have a ring of charge, it has an electric field that's equal but in the opposite direction in the xy plane. And so all the contributions that are in the xy plane are going to cancel one another, and we'll only end up with an electric field that points along the z-axis. It's very similar to the line of charge where the y components canceled with one another, and we only ended up with a component that's along the x-axis or along the z-axis. So that means that we can just simply ignore these, because for every theta value there's going to be a theta on the opposite side of the circle that cancels with it. And so we can just keep the z component so that this vector delta E becomes only a delta E along the z-axis. And I can write that to look like this. And now what I would normally do is I would let my delta theta become very, very small so that this turns into an integral. But there's nothing on the right-hand side here that has any dependence on theta. So even if I turn it into an integral, it's going to become a bunch of constant numbers. I'm looking at a very particular z value as my observation point. The radius of the ring of charge is a constant, q is a constant, and then 4 pi epsilon naught, 2, all those are constants. So all I have is a summation over theta, and I know that I'm summing this from 0 all the way around the circle, so that theta is going to go from 0 to 2 pi. So that just means that delta theta is going to be 2 pi, and that will cancel with the 2 pi in the denominator, so that my total, when I add up all of my delta thetas, my total sum over sum over delta EZ, which sums to the total electric field, is just going to be 1 over 4 pi epsilon naught q z divided by r squared plus z squared to the 3/2.